Before touchscreens, sensors, and error codes took over construction sites, there was a different kind of machine ruling the job. In the 1990s, heavy equipment didn't need software updates, laptops, or warning lights to tell operators what was wrong. These machines spoke a simpler language: engine sound, hydraulic pressure, and raw mechanical feel. No electronics to fail, no computers to shut you down mid-job. Just iron, diesel, and engineering you could trust with your life. Some of these machines are still working today for one simple reason: there was nothing electronic to break in the first place. Let's take a look at 10 heavy construction machines from the 1990s that proved electronics were optional. Number 1. Caterpillar D8R. Early 1990s. The Caterpillar D8R, introduced in the early 1990s, is widely regarded as one of the last truly mechanical heavy bulldozers ever built by Caterpillar before electronics began to dominate machine design. This dozer was created at a time when job sites were harsh, unpredictable, and often hostile to sensitive components. Engineers at Caterpillar knew that relying on electronics in dusty, muddy, vibration-heavy environments could become a liability, so the D8R was deliberately engineered to function almost entirely through mechanical and hydraulic systems. At the heart of the D8R was a mechanically governed diesel engine. There were no electronic control units adjusting fuel delivery, no sensors monitoring throttle response, and no software managing torque curves. Engine performance was controlled through physical linkages and mechanical governors, which meant the machine behaved the same way every single day. Whether operating in extreme heat, freezing cold, or high altitude, the D8R delivered predictable power without electronic confusion or failure. The transmission followed the same philosophy. Caterpillar used a robust power shift transmission driven by hydraulic logic instead of electronic solenoids. Gear changes were firm, reliable, and repeatable. Operators developed an instinctive feel for the machine because nothing was hidden behind computers. If something felt wrong, it usually was, and mechanics could diagnose it without plugging in a laptop. Hydraulic systems on the D8R were equally straightforward. Blade lift, tilt, and ripper functions were controlled by mechanical valves and pilot hydraulics. There were no position sensors or electronic feedback systems trying to correct operator input. This gave the operator direct control and made the machine extremely reliable in filthy environments where electronics would have failed quickly. Structurally, the D8R was massively overbuilt. The main frame, undercarriage, and blade mounts were designed to absorb shock loads and constant abuse. This allowed the dozer to push heavy material all day without developing structural fatigue. Many D8Rs accumulated 20,000 to 30,000 hours with minimal major repairs. The Caterpillar D8R proved that a bulldozer didn't need electronics to move mountains. It needed torque, weight, durability, and honest engineering. Even today, it's remembered as one of Caterpillar's toughest and most dependable machines ever built. Number 2. Komatsu PC400-5. The Komatsu PC400-5, produced throughout the early and mid-1990s, is one of the most respected excavators ever built precisely because it operated without electronic dependency. At a time when competitors were experimenting with early electronic engine management and control systems, Komatsu intentionally kept the PC400-5 purely mechanical and hydraulic, prioritizing reliability over innovation for innovation's sake. The engine in the PC400-5 used mechanical fuel injection with a traditional governor. Throttle response and power delivery were controlled by physical systems, not sensors. This meant no ECU failures, no limp modes, and no mysterious shutdowns. On mining sites, quarries, and large infrastructure projects, this reliability was priceless. Operators could work long shifts without worrying about electronic faults stopping production. The hydraulic system was where the PC400-5 truly shined. Komatsu engineered a pressure-based hydraulic control system that responded directly to operator input. Instead of electronic joysticks sending signals to computers, pilot hydraulics controlled valve spools mechanically. This gave operators precise, intuitive control over digging, lifting, and swinging motions. The machine felt alive in a way many modern excavators do not. Maintenance was another major advantage. When something went wrong, mechanics could diagnose problems through sound, pressure readings, and visual inspection. There were no fault codes to decode and no proprietary software required. Hydraulic pumps, valves, and cylinders were designed to be rebuilt multiple times, extending the machine's lifespan far beyond what modern equipment typically achieves. The PC400-5 became legendary in environments where downtime was unacceptable. It could operate in extreme dust, heat, and vibration without losing reliability. Many of these machines remained in service well into the 2010s, long after newer electronically controlled excavators were retired. The PC400-5 proved that good hydraulic design could replace electronics entirely. It didn't rely on computers to manage power. It relied on physics, pressure, and proven engineering. That's why it remains one of the most trusted excavators of the night. Number 3. Caterpillar 980F Wheel Loader. The Caterpillar 980F, produced during the 1990s, represents the final generation of large wheel loaders designed to operate without electronic management systems. This machine was built for quarries, mines, and large earth-moving operations where electronics were often more trouble than they were worth. Caterpillar engineers intentionally designed the 980F to function using mechanical drivetrains and hydraulic logic, ensuring long-term reliability in extreme working conditions. The engine was mechanically governed, delivering torque through physical systems rather than electronic control. Power delivery was smooth, predictable, and consistent regardless of environmental conditions. The transmission used hydraulic logic to manage gear shifts instead of electronic solenoids, giving operators direct feedback through sound and feel. Hydraulics were equally robust. Bucket lift, tilt, and steering were controlled by mechanical valves. There were no electronic flow regulators or pressure sensors constantly adjusting performance. This simplicity allowed the loader to operate continuously in dusty quarry environments where electronic components would quickly fail. Structurally, the 980F was massively overbuilt. The loader frame, articulation joint, and bucket linkage were designed to handle repeated shock loads from rock and heavy material. Caterpillar assumed the machine would be abused and built it to survive that abuse. Many 980F loaders ran 24/7 in quarry operations for decades. Another major advantage was serviceability. Mechanics could rebuild hydraulic pumps, transmissions, and engines multiple times. There was no software obsolescence forcing machines into early retirement. As long as parts were available, the 980F could keep working. The Caterpillar 980F showed that a wheel loader didn't need computers to be productive. It needed weight, balance, and durable engineering. That philosophy is why many 980F loaders are still earning money today. Number 4. Hitachi EX1200. The Hitachi EX1200, introduced in the early 1990s, was a large mining excavator designed to operate in remote, hostile environments where electronics were unreliable or impossible to support. Despite its size and complexity, the EX1200 relied almost entirely on mechanical engine control and hydraulic logic, making it one of the most dependable mining excavators of its era. The diesel engine used mechanical fuel injection and traditional governors, ensuring stable performance without electronic interference. This allowed the machine to operate in extreme heat, cold, and altitude without requiring recalibration or software updates. Power delivery was predictable, which is critical in mining operations where safety and consistency matter more than efficiency gains. Hydraulic control was achieved through pressure-based systems rather than electronic modulation. Operators controlled massive digging forces using pilot hydraulics and mechanical valves. This design allowed for smooth, powerful movements without the lag or unpredictability sometimes introduced by early electronic systems. The EX1200 structure was designed for extreme durability. The undercarriage, boom, and stick were heavily reinforced to handle continuous heavy digging. Hitachi engineers assumed the machine would run almost non-stop for years and designed it accordingly. Many EX1200 units accumulated enormous operating hours without major structural failure. Maintenance in remote mining locations was another critical factor. The EX1200 could be serviced using standard mechanical tools. Hydraulic components were rebuildable and failures were easy to diagnose. There were no electronic control units to fail without warning. The Hitachi EX1200 proved that even massive high-production mining machines didn't need electronics to perform at the highest level. It remains a symbol of an era when engineering trusted mechanics over microchips. Number 5. Volvo A25C articulated hauler. The Volvo A25C, introduced in the mid-1990s, represents one of the last generations of articulated dump trucks built to operate almost entirely without electronic intervention. At a time when manufacturers were beginning to experiment with electronic traction control, automatic differential locking, and computer-managed drivetrains, Volvo deliberately kept the A25C mechanical, hydraulic, and brutally dependable. This decision wasn't technological conservatism, it was a response to real job site conditions where electronics simply couldn't be trusted. The A25C relied on mechanical differentials, hydraulic logic, and driver skill rather than sensors to manage traction. In mud, snow, loose rock, or uneven terrain, power was distributed through proven mechanical systems that reacted instantly to wheel slip. There were no computers deciding torque split milliseconds too late. Traction happened naturally and immediately. This made the A25C exceptionally capable in off-road conditions where electronic systems of the era often failed or behaved unpredictably. The engine was mechanically governed, providing consistent torque delivery regardless of temperature, altitude, or load. Operators knew exactly how the machine would respond, which made it safer and easier to control on steep grades and unstable ground. The transmission was hydraulically controlled, not electronically shifted, meaning it could withstand shock loads without software errors or limp mode failures. Structurally, the A25C was massively overbuilt. The articulated joint, frame sections, and suspension components were designed to handle repeated twisting and impact loads without fatigue cracking. Volvo assumed the machine would be overloaded, misused, and driven hard and engineered it to survive those realities. Many A25Cs accumulated extreme operating hours in mining, road construction, and quarry work without major structural repairs. Maintenance was another major advantage. Mechanics could diagnose problems using pressure gauges, visual inspection, and experience rather than diagnostic computers. Hydraulic components were rebuildable, driveline parts were accessible, and the machine could be kept running in remote areas with limited support. The Volvo A25C proved that articulated haulers didn't need electronics to be productive or safe. They needed traction, balance, strength, and predictable behavior. That philosophy made the A25C one of the most respected haulers of the 1990s and one of the longest lasting. Number 6. Liebherr LTM 1200. Early 1990s. The Liebherr LTM 1200 from the early 1990s stands as a rare example of a large mobile crane designed to operate with minimal electronic dependency at a time when digital load moment systems were becoming more common. Liebherr engineers believed that safety and reliability came from conservative mechanical design, not from relying entirely on electronics that could fail in harsh construction environments. The crane's drivetrain and hydraulic systems were largely mechanical and hydraulic in nature. Boom extension, slewing, and lifting movements were controlled through hydraulic logic rather than computer-managed flow systems. This resulted in smooth, predictable operation that operators could feel directly through the controls. There were no software delays, sensor failures, or system resets, just physical response to input. Load handling was based on engineering margins and operator training, not electronic enforcement. Liebherr designed the structure with enormous safety reserves, assuming real-world conditions would never match textbook calculations. The boom sections, carrier frame, and outriggers were heavily reinforced, allowing the crane to tolerate off-level lifts and dynamic loading without structural damage. The absence of heavy electronic reliance made the LTM 1200 exceptionally durable in extreme environments, such as refineries, ports, and remote infrastructure projects. Dust, vibration, moisture, and temperature extremes that often cripple early electronic systems had little effect on this crane. Maintenance crews appreciated the simplicity. Troubleshooting was mechanical and hydraulic, not digital. As long as parts were available, the crane could be kept operational indefinitely. Many LTM 1200 units remained in service for decades, long after electronically complex cranes became uneconomical to repair. The LTM 1200 demonstrated that precision and safety did not require electronics. They required thoughtful engineering and disciplined operation. It remains a symbol of Liebherr's old-school design philosophy. Number 7. Case 1150E. Bulldozer. The Case 1150E, produced through the 1990s, is often overlooked. Yet it perfectly represents the era's philosophy of mechanical reliability. Designed for road construction, land clearing, and heavy grading, the 1150E was built to work long hours with no electronic engine management, no computerized blade control, and no digital monitoring systems. The engine used mechanical fuel injection and a traditional governor, delivering predictable torque across all working conditions. Operators didn't have to worry about sensors derating power or electronic faults shutting down the machine. If it started, it worked. Simple as that. Blade and ripper functions were controlled through hydraulic valves and mechanical linkages. There were no position sensors or automated grading systems trying to correct operator input. This gave skilled operators direct control and made the machine incredibly reliable in dusty and wet conditions. Structurally, the 1150E was extremely tough. The frame, undercarriage, and blade mounts were reinforced to survive continuous pushing in hard material. Case assumed the dozer would be used aggressively, often beyond recommended limits, and engineered it accordingly. Maintenance was straightforward and inexpensive. Components could be rebuilt, not replaced. Mechanics didn't need proprietary tools or software, only experience and mechanical knowledge. The Case 1150E proved that mid-size dozers didn't need electronics to be effective. They needed strength, balance, and reliability. That's why many are still working today. Number 8. Komatsu HD785-5 dump truck. The Komatsu HD785, produced throughout the 1990s, was a rigid-frame mining dump truck designed to operate continuously in some of the harshest environments on Earth. Despite its massive size and workload, the truck relied primarily on mechanical drivetrains and hydraulic systems, not electronic management. The engine was mechanically governed, delivering massive torque without electronic oversight. The transmission used hydraulic logic rather than computer-controlled shifting, allowing it to withstand shock loads and constant heavy hauling without software-related failures. Braking systems, steering, and suspension were designed for redundancy and simplicity. Komatsu assumed the truck would operate far from support infrastructure and built it to survive long intervals between maintenance. In mining environments filled with dust, vibration, and heat, electronics were often a liability. The HD785-5 avoided that problem entirely. Mechanics could diagnose issues mechanically, and repairs could be made without specialized equipment. The HD785-5 proved that even massive mining trucks didn't need electronics to move thousands of tons of material reliably. Its longevity stands as proof that mechanical engineering, when done right, can outperform digital complexity. Number 9. Fiat-Allis FD30. The Fiat-Allis FD30, still widely used throughout the early and mid-1990s, represents one of the purest examples of a heavy construction machine that never needed electronics to succeed. Originally designed in an era when reliability meant mechanical simplicity, the FD30 continued proving its value well into the 1990s on large earth-moving, quarry, and infrastructure projects around the world. Fiat-Allis engineers assumed the machine would be operated hard, maintained irregularly, and pushed beyond recommended limits, and they built it accordingly. At the heart of the FD30 was a fully mechanical diesel engine with traditional fuel injection and a mechanical governor. There were no electronic controls adjusting fuel delivery, no sensors monitoring engine parameters, and no control units capable of derating power. The engine responded directly to throttle input, delivering raw torque in a predictable linear way. This made the machine exceptionally dependable in remote job sites where electrical faults could shut down more modern equipment. The drivetrain followed the same philosophy. The transmission and steering systems were hydraulic and mechanical, designed to tolerate shock loads and constant stress. Unlike later electronically controlled machines that protected themselves by shutting down, the FD30 simply kept working. Operators valued this trait, especially in large push operations where stopping meant losing productivity across the entire site. Hydraulic systems were equally straightforward. Blade lift, tilt, and ripper functions were controlled through mechanical valves and pilot hydraulics. There were no automated blade controls, no electronic leveling systems, and no position sensors. Skilled operators could feel the resistance of the material directly through the controls, allowing precise grading and powerful ripping without interference. Structurally, the FD30 was massively overbuilt. The main frame, undercarriage, and blade mounts were designed to withstand constant impact loads. Fiat-Allis prioritized thick steel, conservative weld design, and minimal flex. As a result, many FD30 machines accumulated enormous hour counts without major structural repairs. The FD30's longevity is its greatest achievement. Many units continued working well into the 2000s and beyond, long after newer electronically controlled dozers were parked due to repair costs or software issues. The Fiat-Allis FD30 proved that strength, simplicity, and mechanical honesty could outlast technology trends, making it one of the most enduring machines of the 1990s. Number 10. Liebherr PR752. The Liebherr PR752, produced during the 1990s, stands as one of the last large European bulldozers designed with minimal electronic dependency. At a time when many manufacturers were rushing to introduce digital controls and automated systems, Liebherr took a more cautious approach. The PR752 was engineered around mechanical reliability, hydraulic precision, and massive structural reserves, ensuring the machine could operate reliably for decades without relying on computers. The engine used mechanical fuel injection and traditional governing systems, delivering smooth, consistent power across a wide range of operating conditions. There were no electronic control units monitoring performance or restricting output. This allowed the PR752 to operate reliably in extreme climates, from freezing alpine environments to hot quarry operations. Hydraulic systems were designed for predictability and durability, not electronic optimization. Blade and ripper movements were controlled through hydraulic valves and pilot systems that responded instantly to operator input. This gave operators precise control without the delays or corrections introduced by early electronic systems. Skilled operators could grade accurately and push efficiently using feel and experience alone. Structurally, the PR752 was extremely robust. Liebherr engineered the frame, undercarriage, and blade mounts with enormous safety margins. The machine was designed to absorb shock loads and constant pushing without developing fatigue cracks. This conservative design philosophy allowed the PR752 to remain structurally sound even after years of hard use. Another key factor was serviceability. Liebherr built the PR752 to be maintained mechanically. Components were accessible, rebuildable, and designed for long service life. There were no proprietary diagnostic systems required to keep the machine running. As long as parts were available, the dozer could continue working indefinitely. The PR752 represents the final evolution of mechanical bulldozer design before electronics became unavoidable. It proved that precision, productivity, and safety could be achieved without digital systems. Even today, many PR752 machines remain operational, earning respect for their durability and reliability. Looking back, these 1990s machines remind us of a time when reliability came from simplicity, not software. They didn't rely on sensors to survive harsh job sites. They relied on overbuilt components, mechanical precision, and designs meant to be understood by the operator, not a computer. While modern machines are smarter and more efficient, they'll never match the trust these old workhorses earned, because when everything electronic fails, it's machines like these that keep digging, lifting, and pushing. No screens, no codes, just pure mechanical muscle.